All
Hi,
right.
welcome everyone to our usual Wednesday seminar. And today we have Vasil Dimitrov from the University of Torino, who is going to tell us about the AdS7 black holes and holography.
All right. Good. Well, I'm still struggling with Zoom. Okay. Anyway, yeah, thank you for inviting me. It's a very good to have online seminar like this. So the story that I will tell you is about AdS7 black holes, and those have been studied for a long time, including the supergravity theories. But there are new developments, and this is the plan of the talk. So first, I'm going to introduce the AdS7 CFT6 setup where the story would play out. And then we're going to do the following. We're going to discuss the most general black hole in that holographic setup, which has S1 times S5 boundary. And we're going to do the usual things. Discuss its thermodynamics, supersymmetric and extremal limits, Euclidean on-shell action, and then finally we're gonna do a holographic match with the superconformal index. And in here, the calculation which is new is this part. So it turns out that this on-shell action for this class of black holes is, well, it's technically annoying to compute and nobody had done it. So now it's done. Then I'm going to talk about a new black hole, which is you take the S5 and you replace it with a Sasaki-Einstein manifold. And turns out that this object exists, and you can do all of the same things for it as well. By the way, stop me at any time if you have any questions. I would be happy to turn this into a live discussion. Okay,
Perfect.
so to begin with, I'm gonna first review the supergravity story, and then I'm gonna turn to M5 brains and holography. So we're in supergravity and we're in 11D, and we dimensionally reduce on S4. Okay. So turns out that if you focus on the lowest lying set of KK modes, that is a consistent truncation, meaning that any solution to the 7D supergravity in in terms of those fields that you see right here is a solution of 11D. That's what consistent truncation means. And these two facts were figured out. The supergravity, the 7D supergravity was written down in 84, and the fact that it's a consistent truncation was shown in 99. Then you can do, so that's still quite a lot of fields. So like 14 scalars, 10 one forms. You can do a little, you can simplify your life to the universal sector. So you isolate the U1 squared R symmetry in the SO5. And there is this simpler model, this simpler 7D supergravity is also a consistent truncation, meaning that any solution that we find right here is automatically solution here. Okay, so that's the story. What is the action? It's what you see right here. Like the action is not that important to understand everything, but well, it's not that hard. This is just the bosonic action. It has the two scalars. So the two scalars are x1, xi are my scalars. It has the tree form, A3. Its field strength. It has two one forms with field strengths F, denoted F1 and F2. And this G for me would be denoting the inverse of the ADS scale. Okay, so this mat frag G would be showing in formulas here and there. Now, 11D Maxwell equation imposes the following constraint in 7D. You look at this and you realize that if you hit it with a derivative, it turns into the 7D Maxwell equation that you would derive for this tree form. So why am I saying it as something different? It is different because yes, its derivative is equivalent to the 7D equation of motion. And as such, what I wrote down poses no new constraints on the dynamics, but it is reducing the physical degrees of freedom of this gauge field by a half. Okay, it's like a star of the thing, and then the thing reduces the degrees of freedom by half, but no new dynamics. That would be technically important in the actual calculations. I just wanted to mention some where the bodies are buried. Okay, so what is the M5 brain picture? So you take your stack of n M5 brains, and you're in flat space. You construct the following famous solution, where your G here is the gauge field in 11D, and the field strength in 11D, and it has flux through the S4. Okay, we're doing a dimensional reduction on the S4. You write down this background, and you take the near horizon limit. In the near horizon limit, your stack of n M5s is equivalent to 11D supergravity on AdS7 times S4, and with n units of flux. But we just showed that the 7D supergravity that I introduced is a consistent sector of this 11D theory. So here now, this is your AdS-CFT setup. You have your 7D supergravity, and that is dual to 6D 2,0 superconformal field theory on the world volume of the brains, which has SO5 R symmetry. SO5 is the symmetry group of S4, so this S4, and it shows up in gravity as the internal space and in field theory as the R symmetry. So far, everything is canonical stuff. Now, you might ask, what is the most general black hole that you can construct in this setup? Well, let's take the bosonic part of the superconformal symmetry group of the 6D theory. Okay, so that's the superconformal symmetry group. It's bosonic part. And now I'm gonna take this theory and I'm gonna put it on the real line times S5. I just like this background. I put my field theory here. This group breaks to the following, to R, then SO6 coming from here, and the SO5 coming from the R symmetry. Now, SO5 has cartan U1 to the power 2, and SO6 has cartan U1 to the power 3. And then I count the number of charges I expect, and I get these total 6 number of charges, 1 energy, 3 angular momenta, and 2 electric charges. So the most general black hole I should envision in this theory would have all of these distinct from each other. Now, for the rest of this talk, I'm going to work entirely in Euclidean signature. That is, I would take time and I would weak rotate it as such. And now the question is, can we find solutions of the 7D supergravity theory that I wrote down, which have the following isometry? So it's just U1 to the 4, but I have kind of indicated what each, with which coordinates are going to be denoting each of my U1s. So tau is the Euclidean time, and 3 more angles parameterizing these guys here. Okay, so can you find such a solution? The answer is yes. It is notoriously difficult to find this solution, and it was only recently done in 23. Different limits of this solution have been known, for example, like equal angular momenta, equal charges, or 2 of angular momenta set to 0, something like this. But the most general item was only recently discovered, and I would not write it down because it's just nasty. Like it would not tell you anything useful. What you need to know is that I'm using these coordinates, Boyer-Lindquist coordinates, and tau is time, r is the radial coordinate, the phi's are the 3 U1 angles, and mu's are essentially polar angles. And the black hole looks like this. At infinity, it looks like empty AdS with, of course, corrections. So this is the metric of empty AdS. This is just the S5. And then nearby the horizon, it looks as a familiar thing. It looks like a rotating black hole with temperature, inverse temperature beta, and angular velocities capital omega turned on. And so this is the near horizon limit. No, sorry, not the near horizon limit. This is how the geometry looks like nearby the horizon. And from here, you see that this space is only smooth if you demand the twisted identification. So you take your time and an angle, and if you like twist them like this, they should be like go around the time circle once. You also have to go around the angle once. And also the angles are separately 2 pi periodic. So this is the usual Gibbons-Hawking story for rotating black holes. Now, in between, it's awful, but at the edges, it looks exactly as you expect. So, and the important point, this black hole is not supersymmetric, and it is not extremal either. Okay? Good. So, now, in addition, holography is teaching us that you set up your boundary conditions at infinity, and then you have to fill up the space-time with regular stuff. Like nothing should blow up. The metric doesn't blow up. We already saw that. But also we should demand that the gauge field doesn't blow up. Any contractions of the gauge field at the horizon should be finite. All of this amounts to saying that if the horizon is generated by this Killing vector, it must be that the contraction of this Killing vector with all of the gauge fields on the horizon vanishes. And this is ensured if you do the following. So, so this wording here is a little bit frustrating, but I will explain. So these are the original gauge fields in which the black hole was written down in 23. These gauge fields at infinity, they go to 0. Okay? So that's what I mean naked. To properly regular gauge fields are not these. Instead, you have to gauge shift them. So phi here is a constant. This is what originally the gauge field 1 was, and now this is the new gauge shifted gauge field, which is denoted by a hat, and it is regular. And now this condition here is kind of simple because you contract a one form with a vector. That's easy. Here you contract a three form with a vector, and demanding that this is 0 is a complicated system of equations that you have to solve. It's not just like one relation, but you work a little bit and you find that this works. This kind of like combination of gauge shifted tree form does the job of being regular at the horizon. This A2, I'm not sure if I explained carefully. Let me return here. This A2 is an auxiliary field. It does not show up in any, like, does not have a kinetic terms, like, it's just pretty much irrelevant for our story, but it's important for the complete description of the 7D supergravity. So these are my now good gauge fields to work with, and those are the ones that we're going to be using. Okay, questions so far?
No, so far no questions.
Okay, perfect. Now, in that case, we can now, so far, we geometrically determine the potentials. This is what you saw appearing in the metric and in the gauge field. These items are determined as some expressions in terms of whatever parameters you chose to write down your black hole with. And I kind of like schematically wrote them like this here, but they're not arbitrary expressions. They depend on what's happening inside. Okay, and what's happening inside is very explicitly written down in the paper. So you determine those guys geometrically. by regularity. And the charges you calculate by, like, you open your favorite GR book and you do some Komar integrals and you define the ADM energy and you just derive those charges, also written in terms of whatever the black hole was written down in terms of. And now all of these objects, they have to satisfy the so-called quantum statistical relation, which is saying that the Euclidean on-shell action should be given by the entropy, area over G, which you can also calculate geometrically, and this combination here. And now you want to verify if this is true. But notice that this equation is kind of ambiguous. It is true, and you'll see that it is, but upon adding arbitrary finite counterterms, when you evaluate the energy, those finite counterterms, they're only going to be relevant when you're evaluating the energy or the on-shell action. And when you add such finite counterterms, what is happening is that the energy is changing to be the energy how it used to be before, and now it's just modified. The on-shell action is not independently modified. It is also modified in the similar fashion, just multiplied by beta, in such a way that the quantum statistical relationship is still holding, but now what you called energy and what you called action are different. So all I'm saying is that neither the energy nor the on-shell action are well defined in principle, and there is no that these are just scheme dependent objects, and that's life. Okay, so this is just a remark which will be important in a second. And now what do we want to compute? So you take this action here, the bosonic part, and you impose the equations of motion. It's a little bit of algebra to show that it collapses after equations of motion are being imposed on shell. It collapses to the following expression. So it is total derivative of something regular, and that's crucial, and I'll explain in a second. So first of all, I have this like integral over the 7D space, which is remaining, and I have a total derivative of something regular. Now, if I was to stupidly rewrite this such that this item here is not regular, I would not be able to simply use Stokes and say this is just a boundary term. The fact that we worked hard to rewrite it as something regular means that this is a boundary term, making the evaluation easier. So notice the appearance of this hat here, like a hatted potential, which means it's regular. Everything that's here in this expression, which I just omitted, but like you can find it in the paper, is involving only hatted potentials, only hatted 3-form and 1-form, which is important, okay? This is one of the things that you have to be careful if you're doing such calculations. Now, of course, this object is divergent because you evaluate this from all the way to infinity, and it diverges. Now, we know how to deal with this for a long time, and what you have to do is holographic renormalization, and you add the following boundary terms. So this is divergent, you add something else which is divergent to it, and this something else involves the curvature of the induced curvature, the Gibbons-Hawking-York term, and it involves now these three terms, which go like no powers of r, 1 power of r, 2 powers of r, where curly r is the Ricci scalar of the induced metric of the boundary. And so you calculate this object, and that would ensure that the answer is finite and physically sensible. You got to do that. That's a must. But as I told you, there is scheme dependence. And you can also add the following items. You can add arbitrary linear combinations of anything involving curvature on the induced metric to the third power. So you can do r to the 3, you can do this, you can do this. You can add all of these items, and each of them will be finite. So it will not introduce divergences, but it will modify your answer. It would perform this operation. I goes to I prime. Okay. Now, of course, like you don't just add whatever you want here. In terms of finite counterterms, you probably want some physical requirements. You want them to be diffeomorphism invariant. You want them to be gauge invariant. You want them to respect the symmetries of the theory that you're studying. What I wrote down here are some diffeomorphism invariant objects, and they do not involve the field strengths. This list is non-exhaustive in the sense that I can also imagine writing down terms involving the field strength, introducing even more coefficients, and there's like you can in principle do this, and in more complicated situations you might actually need to. In this case, we didn't. And the reason is that for this special case of S1 times S5 boundary, those 6 items that I wrote down, they are actually linearly dependent. So it's perfectly okay to set all of the coefficients to 0 except 1. And that is enough for our purposes, but I stress again that in more complicated situations, you might need to do a little bit more than that. So you add these finite counterterms, and you have to sum these 3 integrals and see what you get. Okay. Good. Now we're going to do a little bit of a pause of this calculation to discuss our field theory expectations. So we're going to do a gravity computation, and we kind of want to know what the answer should be a priori. So let's see what the answer is. Holography tells us that this, whatever we're calculating, should be the large n limit of the superconformal index of the dual field theory. So I take my 6D theory and I put it on S1 times S5, and I write down its superconformal index. I do the large n expansion, and then something which was discovered around 2018 and like papers following after that was that one should go to what is known as the second sheet. So this index is written down in terms of some fugacities. I have dressed the index with some numbers like which are multiplying the conserved charges. And so the omega hats are denoting the possible twistings between the S1 and S5. So this is only topologically, it's a product like this. It's actually a twisted product, can be in most general. So these omega hats are denoting these twistings. And the delta i's are denoting the values of the background R symmetry. So you have like this theory has an R symmetry. And as we discussed, generically speaking, the R symmetry is SO5, but I'm only considering the cartan of SO5. So like I only turn on fugacities for the cartan generators as per usual. And then the answer is as follows. It scales as n cubed, where n is the rank of the gauge group. And then it has the following expression in terms of the fugacities. These expressions, now a little bit of like how historically it happened, when these objects were first derived, these fugacities were set to be equal to 0. And then actually, let me not go into that story, but I just want to emphasize like the two different cases. What I mean by second sheet. Second sheet means that these fugacities, they should sum up to 2 pi I n when n is an arbitrary integer. And the terminology first sheet means n equals 0, and the terminology second sheet means n equals plus minus 1. Okay, this is just the terminology that I'm going to be using. So you find this expression, and this is what you want to compare with. Now, this is written in terms of field theory variables. So let's do a little bit of holographic dictionary exploitation. So in the conventions that we have been using, the Cartan generators of the SCFT, so that is the deltas and like whatever couples to the deltas and the omegas. These generators, I will be denoting them by a hat, standing for field theory somehow. And they are related to whatever I calculated in gravity, the charges, meaning the energy, angular momentum, and electric charge, with these simple factors involving the AdS radius. Now, I combine this with the twisted identifications that I get from the bulk, because it's a black hole, it's regular, it has some twisted identifications, and I look at how the fields behave when I go to infinity, and I identify the currents and like how my gauge fields behave at infinity. Out of my gauge fields, I build my currents, I build my superconformal algebra, and like if you do it carefully, you realize that you map the map between field theory variables and gravity variables. It's quite simple. So you take the field theory omega, and it is what we already computed, beta, and this capital omega. It's this expression. And you take the field theory fugacity delta, and it is related to what we already computed, beta and phi, in this simple fashion. Let's give them names. Let's give them omega without a hat, which is now a gravity variable, and var phi, which is also a gravity variable. So these are my important gravity variables. And finally, I have to do a simple calculation. I calculate the flux through the S4 in 11D. I mean, I remember that all of this is embedded actually in 11D. So I have to, in order to describe the proper microscopic origin of the constants that appear in my supergravity, I have to remember how I'm embedding this in 11D. So I calculate the flux through the S4, and I obtain this simple relationship between G Newton and n cubed. So in gravity variables, 1 over G Newton is n cubed for this holographic setup. Okay, so you do that, you take your answer that field theory tells you, and you convert it to gravity variables, getting the following expression. Okay, so it has the volume of S5, and it has these particular combinations of the thermodynamic potentials that we calculated. So that is your expectation. Now you have a target. So let's see if we can meet this target. Good. So continuing a little bit with the overture, there is this prescription that surfaced around 2017, 2018 of how you should be calculating Euclidean on-shell actions of supergravity solutions. Because if you just take an extremal solution and you want to calculate this integral, I mean, like I give you an extremal black hole with a 0 temperature, and I want to calculate this integral. Okay, clearly I would have divergences coming at infinity. We already discussed those, so this is divergent. So I include those guys to make sure that my answer is finite. However, famously, black holes at 0 temperature have an infinite AdS2 throat, which means that, in fact, I have a divergence from the lower bound of this integral as well. So the integral is divergent in two ways. Like here, it's divergent at infinity, and it's divergent down there if the black hole is exactly at zero temperature, which prompted the desire to work at supersymmetry, but not extremality. So now there is a question. Under what conditions does there exist a Killing spinor in the supergravity that I wrote down, which solves the Killing spinor equations? This is annoying to prove, but can be done and leaves a very simple result. A Killing spinor exists, meaning that the background is supersymmetric. So the theory is always supersymmetric, but it's another question if the background is. And the background is supersymmetric, provided that the charges that we calculated sum up to zero with these particular coefficients. And that statement is equivalent to the following statement, that that this particular combination of potentials of omega, phi, and so on, and beta, is equal to plus minus 2 pi I. Okay, that is purely gravity analysis. There is no field theory going on here. This is just, does a Killing spinor exist? This relationship is already reminiscent of what field theory is saying about how the fugacities are related. So this should ring some bells. But beware the complex nature of what we're doing. Everything is intrinsically complex. So that means your potentials, your charges, entropy, metric components, and gauge field components are intrinsically complex. Okay? And moreover, it's not just lazy weak rotation. I mean, you know that you take a rotating black hole and you weak rotate, and because there is a cross term between t and an angle, that would introduce an I. But you can go to what's known as real Euclidean section. That is, you take some of the parameters in the solution, like a rotation parameter, you weak rotate that one as well, and now that gives you a real metric to operate on. What I'm describing is more complex than that. Even if you try to weak rotate some of your parameters, there is no way that you're gonna get a real metric. So this is a complex solution to Euclidean supergravity. That's the fully correct words to say. But this solution is useful because now you can carry on with it, and you can take the extremal limit. So that's the slogan. SUSY first, extremal later. You've done the SUSY limit, and now you can you can safely drive beta to infinity. That is, drive your temperature to zero, and this is happening in such a way that these combinations, omega and var phi that we introduced, remain finite. But they're still complex. That's important to keep in mind. However, what you physically would measure, entropy, angular momentum, charge, entropy, and also like this, you will not physically measure this, but just to mention that these components of the metric and the gauge field, everything becomes real, including the entropy. Okay. Entropy becomes a famous expression that you see in like black hole literature. There is always a square root involving the charges in some fashion, and that is your entropy at the BPS point, where BPS for me means extremal and supersymmetric simultaneously. Okay, so this story is really surfaced in 4D and 5D, and I'm kind of repeating it here, even though there is no surprises, just because, well, I think it's a cool story and important. But yeah, so the main story of these papers is repeated in 7D, and it's, I think, a general story. Okay, now, with all of this, we are ready to calculate, come back to our original goal. So remember these three expressions: bulk counterterms, divergent counterterms, and finite counterterms. Now we have to sum them up and take the cutoff. So cutoff here means the UV divergence, so the divergence at infinity. You sum those guys up and you take the limit to take the cutoff to infinity, and the answer remains finite. And this is your Euclidean renormalized on-shell action. In our case, it depends on this coefficient C1 because we kept C1 in the game. I mean, like we killed C2, C3, all of these, but we kept C1 in the game. And it's a finite answer. And the answer looks like this. Okay? It has this factor here, and then it has this additional piece. Now, we go back to our expected answer, and we notice that our expected answer is, oh, I forgot to ask you, are you seeing properly when I move my mouse? Because I do that a lot, thinking that you're aware.
Yes, we do.
Perfect. Okay, good. So this is the expected answer. And what you calculate from gravity is this instead. Now, that you clearly have the inclination to set C1 to 1 over 25600. And you're allowed to do that. That would be effectively picking a scheme. You're not allowed to set C1 to depend on the parameters of the solution or to depend on any of the potentials or to have like to be anything like physical. Okay, C1 should be a numerical constant. And there is a clear choice of a numerical constant that selects a scheme in which whatever field theory is telling you the answer should be, gravity agrees upon. Of course, in the supersymmetric limit. I mean, this Euclidean on-shell action, we can actually calculate it away from supersymmetry, and it is not going to be that simple expression. It's going to be a horrendous expression that you can find in the paper. In the SUSY limit, it simplifies drastically to this. Okay? And there is a scheme that matches with holography. So because I'm not receiving enough questions, I'm going to ask myself questions and I'm going to answer them.
So I actually had a question. Can you remind me? So the small g, the small g to the power of 4, what is that?
Yeah. Oh, so
Actually.
this matfrag G is just inverse of the AdS scale.
Okay. So yeah, can potentially C1 depend on the AdS scale? No, it cannot because it's scaleless.
Yeah, so it depends on what you mean. Can it depend? I have, in principle, yes. In principle, C1 does depend on the AdS scale, but I have kind of like isolated the AdS scale here. You can see this from dimensional analysis. So basically, let's take a look at some terms. So this is 1 over G, and it's right here. Like this, I don't know what's the dimension of this. Well, I guess it has to be dimension of length, of inverse length. And now let's take a look at the counter terms that you have to include. So it goes like length, and then from here you can determine that the dimension of Ricci is like it goes as the dimension of Ricci is 1 over length and so on. So you can see kind of like how the powers do. Like it's AdS inverse AdS scale, 1 over in the inverse AdS scale, 1 over inverse AdS scale to the power 3. And so if you want to build a cubic terminar, you have to do 1 over G to the 5. Okay, so the way I've written it, C does not depend on G, right? But in principle, it is indeed okay. So I guess my statement was a little bit incomplete. Like the correct statement is that these coefficients should only depend on little g, but I have already done that, and they should not depend on the any of the variables that specify my solution. Okay.
Okay, yes, I see.
Yeah.
Just one more thing. So actually, returning to the holographic renormalization, Why did you omit all the derivatives of Ricci and so on? Because your boundary is just a sphere, right?
Yes,
Okay, yeah, then I see, yes.
but okay. So just because you mentioned it, let me
Oh,
emphasize
yes,
that.
sorry. You had C4, C5, my bad. Just I
Yeah.
missed them, yeah.
So yeah, and let me of course emphasize that these integrals, they're not calculated at the asymptotic boundary. Okay, so even though here it says boundary of the manifold, this is not what I mean. This is really done like a little bit before the asymptotic boundary, which is the way that this thing carries divergences to cancel those divergences. It's just done in the induced metric, a little bit away from the actual boundary. And um, so of course I have those guys, okay, and they're non-zero and they are potentially important, but when we evaluate them, okay, so this is for the divergent ones, but for the finite ones, sorry, for the finite ones, you're absolutely right. This is evaluated at the actual boundary, and like you might want to say, okay, I should include them, but they all amount to the same. They're all the same in this background. They can be different in principle. So, as I was saying, for a more complicated boundary, you might need to actually include those with distinct coefficients. But it just turns out that if you evaluate this one, it is the same as this. So you might as well just kill C2. This is like a simplification for our case. Yeah. That is completely consistent to do.
I see, thanks.
Yeah, good. Okay, so here we are, and now there is a scheme. There is a scheme which agrees with holography, such that what I calculate in gravity is exactly what the large n of the field theory partition function is saying. Now, what is the scheme? There's in the literature, the people have been using various schemes and discussing various finite counterterms. The one that I'm using is such that the partition function of the supersymmetric field theory, or the superconformal index, which is usually related to the at large n, this becomes the e to the minus on shell action. And sometimes people write this supersymmetric Casimir energy as a prefactor in front. Okay, you see this type of expression in many papers. The scheme that I'm using is such that this is zero. I'm not, and it's very important to say that all of these being scheme dependent, there is no like it's unclear if there is a unique scheme that would fit all. Okay, the one that I'm using is such that I have set this to zero because I directly match the action that I calculated with the minus log of that of z, which means that I'm kind of like implicitly setting this to zero, or alternatively said, in probably more understandable fashion, is that if I use the scheme with c equals 25600, and I evaluate in this scheme the on-shell action of empty AdS7, I would get zero. Okay. This scheme is very familiar to background subtraction. It amounts to whatever background subtraction is doing, but it is now here implemented through holographic renormalization with these finite counterterms. Okay. Now that's the end of the first story, and I'll pause for questions. In case none, let's move on. So the second part of the talk is about generalizing this black hole to more general setups. And to do that, I would not go into huge detail explaining what's happening on this slide. I will just tell you that there exist these 5D manifolds called Sasaki-Einstein, which obey the following three properties. They're Sasaki, they're Einstein, and they're Calabi-Yau. And you demand all of these, and that kind of like restricts what the metric can be, still leaving a huge freedom. And now you look for solutions and you find some. So the first solutions of this type are in all the way to 84, but they're not particularly interesting. Well, okay, and they're interesting for on their own right, but the really spicy ones came out in 2004 and were immediately generalized 1 year later to this LPQR, which is this here P, Q, and R are three parameters of that solution. So that is some object, which in the case of LPQR and YPQ, I guess, this is topologically the same as S2 times S3, but it has like some non-trivial information happening inside apart from the topology, and it is specified by these three parameters, P, Q, and R, which satisfy certain regularity conditions. Good. So these manifolds exist. They're extremely useful in holography and in like supergravity string theory, and have. Now the question is, can we make use of them in our story? Now, remember that the previous black hole that I showed you used to have S1 times S5 boundary. Now let me take the S5 and let me write it down in the following suggestive fashion. Okay, so I introduce one form sigma, which is dual to what's called RIB in Sasaki-Einstein language. So well, okay, I do not have a particularly nice slide on this, but so I view the 5 sphere as a vibration of an S1 over CP2, where CP2 has the following explicit metric, where sigma 1, sigma 2, and sigma 3 are the left invariant Maurer-Cantan forms, and it is fibered. This coordinate psi is fibered over this 4-dimensional base in this fashion. And that's just a rewriting of the vanilla S5. Now, the LPQR space, which is topologically distinct from the S5, admits the following way of splitting it up into a fiber and a base. And the base is different. It's not CP2. It's something much more complicated involving these P, Q, and R. And the fiber is more difficult, it's more complicated. And I have not written them down, but they're explicit. And with this slide, all I'm saying is that there is no like a continuous way to deform the S5 into LPQR, obviously. I'm just saying that like on a practical level, when you do calculations, you see this metric and you just go and artificially replace sigma with sigma tilde, and you replace the metric of CP2 with the metric on the base that you need, and you would get LPQR manifold. And so that's kind of like a trick that we used in the following way. So what you see here is the field configuration of the black hole that I showed you before, except that now actually I can fit it on one slide because I have set the angular momenta equal. Okay, that dramatically simplifies the solution and makes it into a form that was written like maybe 15 years ago. I don't know exactly how many. So this equal rotation limit of the BDHM black hole looks like this, and I don't want you to like read too much into what's going on here, except notice that here I have the CP2, and I have the sigma, the fiber over the CP2. Of course, the S5 is just this, but the black hole is not just this. That's the full geometry, the full non-supersymmetric geometry, which at infinity, it will become sigma squared CP2. Like if I take the radius at infinity, it will become exactly S1 times S5. But this is how these objects appear in the geometry, in the full geometry, and that's suggestive because now we can do the simplest possible thing. We do the replacement. We take sigma, move it to sigma tilde, we take the base, we move it to the base of LPQR, and there is no guarantee that what we're doing should work. I mean, this is kind of like guesswork at solving Einstein's equations without actually solving them. You do that replacement and you check equations of motion, and they work, okay? So now you have a candidate solution, which is new. And to really guarantee that this solution is like a properly well-defined object, you have to do some regularity analysis, but the regularity analysis is not significantly different to what has been already done in the literature. So you go around, you finish your homework, and you declare that you have found a new configuration, which is just this in the equal rotation case, which now has, instead of S5, has LPQR boundary, okay? So this works. And it is just, let me completely mention that this is still fully non-supersymmetric and non-extremal. Now that you have a background, you can play the game and calculate the thermodynamic quantities. So you calculate, so with tilde now, I would be denoting the quantities after I made the modification. So that is the LPQR case. And without tilde, it's what we calculated before for BDHM. So the following is true. You calculate all of the charges again, and they are just proportional to what you calculated before. And the proportionality is the volume of LPQR over the volume of the S5. Okay? You do this, and that means that the quantum statistical relation holds in the following fashion. So the potentials do not change, but all of the charges just get multiplied by a factor. Now, you might say that this sounds a little bit trivial, and I would disagree with this because the topology of the space has completely changed. Okay, the topology of the space is no longer S1 times S5. It is just the calculations are very similar in the local calculations, the local expressions are similar, but the topology is completely different. And we kind of get this simple thing analysis for free after we have done the other analysis. Okay, so there is your constant relationship. And now we do the same as what we did in the previous case. We ask if this, under what conditions this object is supersymmetric. And the conditions are very reminiscent of what was happening before. Existence of Killing spinor means that the charges sum up to 0. Now these are the tilde charges. And that the potentials are plus minus 2 pi I. And with this, even though this solution that we found exists exists at not at the supersymmetric point or the extremal point, we can take the limit to supersymmetry, in which case the on-shell action simplifies exactly as before. But now, instead of the volume of S5, so in the previous expression, the volume of S5 was sitting here. Now it is the volume of LPQR sitting here. Okay? And now, this is your result. What does field theory say? Does field theory say the same? To get the field theory result, you have to take the partition function of the 6D theory, and you have to take that theory and you have to place it on S1 times LPQ. You do that, and then you open the literature. Those people here did that, and they wrote down the index, and they computed it at large N, some caveats, which I'm going to mention in the next slide. But this paper here, using a different approach, which is consistent with the large N analysis at leading order, obtained the following expression. So now you stare at this and at this. You remember your dictionary, which related phi's to deltas and omega without a hat to omega with a hat and G Newton to n, and you realize that these expressions are the same. Notice that here I'm using exactly the same scheme that I defined before. Okay, so that is to say that I'm using the same scheme to evaluate the on-shell action both of the S1 times S5 boundary and the S1 times LPQR boundary. Of course, yeah, I'm just going to mention this in the next slide. Okay, so this is your if you wish, another exciting holographic match for a novel black hole. Good. And now we can go to, I want to make some comments. So the first one I already emphasized that this LPQR space has a distinct topology compared to S1 times S5. Now, another comment is that if I take a look at the symmetries of S1 times LPQR, remember that, okay, so this one is topology S2 times S3, which means that I also, once again, have three angular momenta, one sitting here and two sitting here. So in principle, there should exist an even more general black hole with three unequal angular momenta, which has this boundary. Okay, it should exist because it's kind of like by symmetry, it should be around, but it is much harder to find. Okay, to find this black hole, this trick of writing the metric as such, the full metric, and just doing the replacement would no longer work. Things just don't separate that nicely. As soon as you start having angular momentum, distinct angular momenta. So this black hole, bear me, it's still rotating, but all of the angular momenta set equal, which simplifies the analysis. If they're not set equal, this trick would not do the job. Which is why this is much harder to find as a solution to Einstein's equations. But okay, it would be nice if somebody with smart idea comes around and finds this black hole. Now, as another comment, this result that I showed you constitutes a prediction for the large N of the superconformal index. And by prediction, I mean that the field theory calculations that I have been telling you about are have been done under some simplifying assumptions and under some caveats, and like they're very legit in terms of what was computed, but a little bit more work on the field theory would be required. And now there is a gravity target, if you wish. And then the other comment is a little bit subtle, but in the case of S1 times S5, there exists a smooth supergravity background, which is dual to the vacuum of the CFT. And that's just empty AdS. So you take your S1 times S5 boundary conditions and you fill it up with a manifold which caps off smoothly and does not have a horizon. And the simplest thing you can do is just AdS. It does not have a horizon and it caps off smoothly. And this is supposedly the vacuum, not supposedly, this is the vacuum of the 6D theory placed on S1 times S5. Now, we have found a black hole with S1 times LPQR boundary, but if you don't want a black hole, and if you just want to fill up that space without a horizon, fill it up smoothly, there is no known smooth solution, okay? Which kind of like leaves a puzzle about what is happening with the partition function of this theory, evaluated, if you wish, on the first sheet, not like, or just basically what is the vacuum of the field theory placed on this background depicted with geometrically. And finally, just want to mention that a similar story to everything I told you exists in 5D. The finite counterterms, the extension to S1 times LPQ, in that case, not LPQR, LPQ. But that story is a little bit simpler, and I decided to omit it. And I think that's all I have.
Okay, so let us thank the speaker. And questions?
Okay, thank you for the talk. Can I ask a question like this? What is the convenient purpose of these calculations? I mean, you want to calculate superconformal index on different backgrounds or something, or vice versa. It's interesting to learn something about black holes.
You mean you're asking, do I have a field theory motivation or do I have a gravity motivation?
Yeah. The best motivation. What is yeah?
Good. Well, I guess the motivation is two ways. You have this holographic conjecture and you wanna test it. You wanna test it on the most non-trivial things that you can think of. And of course, nobody in their right mind would expect that something would fail, especially at leading order in large N. But building up test grounds for rigorous tests is a useful thing.
So you want to like perform both calculations and compare still.
Yeah.
But is there a use for each and every calculation, like calculation on the black hole side separately and on the safety side separately? Is there an application, I mean, of this one or that one, or
Right. I mean, depends on what you want to do. I mean, like in this case here, we did a gravity calculation on this non-trivial background, S1 times LPQR. But the field theory, and let me pull out the slides. Again, okay, so here we are. Now, the field theory here, I told you that, that this thing has been calculated in field theory, okay? But I lied a little bit, yeah? Because what you have to do in field theory, I mean, like, it depends on what you mean calculated. So when you put your field theory on a specific background, you write down the superconformal index and you use supersymmetric localization to convert it into a matrix integral. But that's not, you're not done. Now you have to take this matrix integral, which is written explicitly as an integral over the gauge group, and you have to evaluate it at large n to match with holography. Or like the leading order in large n would be two derivative supergravity. The subleading orders in n would involve higher derivatives in gravity, and that's extremely useful to have. Like if you care about like higher derivative corrections, that's something nice to have. But for now, we're focusing on just the leading part. So that's what you have to do. That's the prescription. Those papers here, and also in addition, if you want to describe black holes, you have to go on this second sheet that I was telling you about. So I was making distinction between first sheet and second sheet. So this paper, 2015, they didn't go on the second sheet. Okay, they calculated something, but not on the second sheet. So this paper right here used different method, not what I described, known as the Cardy limit, to obtain this expression. Okay, so now you have a gravity result, and that would instruct some calculations happening in field theory. Like usually, like in my experience, usually it's the other way around. Like I like somebody tells me something in CFT, and I go and try to reproduce it in gravity. But in this case, there is it's a two-way street. I'm not sure if I'm answering your question satisfactorily.
You actually always answer like let us calculate one and the same thing in holography and in CFT, right?
Yes.
So the logic is always like let us again check the conjecture. So my question was like, what is it if we inverse all this stuff and try to implement AdS7 to calculate something? So the question is, what can we calculate with? Yeah, probably something interesting in gravity or in safety, something. I mean, very naive question, probably.
Right. Well, good. So again, my answer is only going to be based on what I know. Probably somebody else would have a better answer. But something that I'm quite comfortable with is gravity is an effective theory. And in principle, being an effective theory, I can imagine adding higher derivative corrections. And in fact, I should. Like Wilson tells us that at different energy levels, the theory behaves differently. So I go like one level up in energy, like a little bit higher, and I should see new degrees of freedom. In gravity, the way that these new degrees of freedom show up as higher derivative corrections. Now, I that argument does not tell me what coefficients do these terms have. Okay. Now I have to use something UV complete to tell me what these coefficients are. I have two options. If I'm in flat space, I can use string amplitudes to kind of like start fixing those coefficients and like give a correction. If you're interested in modified gravity, for example, like that's some UV complete theory to be working with higher derivative corrections. In the case of in the case of asymptotically AdS spaces, it's much harder to fix those higher derivative corrections. And calculations on field theory side at subleading in large N can actually start doing that for you through holography. And then this is something that you're not testing holography, you're using it. Okay.
So you basically will extract the higher order corrections from CFT data. Okay.
Yeah. Instead of string amplitudes, for example, this is just one test case that I'm familiar with during my work, but I'm like, yeah.
Okay, thank you.
Okay, so I have several questions, comments about constructing the solutions. So, first of all, those LPQR spaces, is it the same as length spaces? LPQR.
It is the kind of like the analog of length spaces in 5D. Like so I here kind of like hinted that a similar story can be done in 5D, in 5-dimensional gravity, in which case the boundary is S1 times S3. And I can take the S3 and I can replace it with LPQ. Yeah?
I see.
So here what I'm describing is I have a boundary which is S1 times S5, this S5, and I'm turning the S5 into LPQR. So these are the analogs in 5D, but let me just mention that they're different than they're more intricate, as you know, than just the length space.
I see.
Yeah. But that's exactly the analogy that I'm alluding to. That something similar is happening in 5D. And this black hole in 5D with S1 times LPQ boundary and correspondingly S1 times LPQ horizon was not something that had been written down in the literature before. I think because it's kind of like a trivial thing to do.
Yes, it's taking a factor group.
Yeah. So nobody bothered to write it down. Of course, we wrote it down for completeness, but the 7D story it's different due to this topology change. This is actually like actually new. Yeah.
I see. Yeah. Well, speaking about the construction of supersymmetric solutions in one of your previous slides, Yeah, I mean, usually one does following the killing spin and bilinears procedure, the classical one by Gauntlet, Gutovsky, Real,
Yeah.
a lot of other names. So, was it done for 70 supergravity? Like, because then you naturally have a Kähler base or Sasaki-Einstein, Kuhn Sasaki-Einstein, or
Yes.
Sasaki base. And then you can assume some nice properties like usually you want the scalar base to have some really strong integrability properties. Like
Yes. So yes, those are very good questions. I'm not sure how much of this analysis had been performed explicitly. And this is just my lack of knowledge, not anything else. I think there are some partial results maybe on how to do what Gutowski and Real did in 5D for 7D. And such a structure with the bilinears and the Kähler base should exist, and like, surely it exists, and it is a great workplace to start looking for 7D solutions. Okay.
mhm.
We didn't do that because we were lazy and we just did guesswork. Instead, we just guesswork the solutions to the equations of motion. Notice that I never actually explicitly constructed supersymmetric solutions.
Yes, actually, yeah, this was another question of mine. Like, so did you construct the killing spinner? How did you check that the solutions actually admit a supersymmetric limit?
Good. So the with in the paper we did not do that. However, let me emphasize that this analysis for this black hole, this BDHM black hole
Mm-hmm.
that I'm discussing. So here I said the following. I said that the existence of Killing spinner is equivalent to those conditions. Yeah. This has been explicitly checked in
Mm.
papers by Cvetic, Lu, Pope, like the usual gang. For the case, like for example, they consider a case of equal charges or equal rotations, I don't remember. And in that case, you sit down and explicitly do it, okay? So we haven't done that in the paper with full honesty,
Mm-hmm.
but the calculation it's one of those things that is guaranteed to work, okay? This is surely a supersymmetric solution. It agrees perfectly with a supersymmetric superconformal index from holography. This is just bound to happen. It's just annoying to sit down, construct spinors, and we did not bother. But that said, it is very important to do it, and the correct way to do it is the formalism that you described. You have to split into bilinears, Kähler base, so on, so on.
Mm-hmm. I see. Um, yes, and the statement that the existence of the killing spinner is necessary and sufficient for the conserved charges for the Komor integrals to satisfy the BPS condition. Where can how was it shown and where can I see the proof? Where can I find the proof?
Well, yeah, good. So again, this is a little bit of lack of knowledge on my side, but I don't know for a gravity proof. I just know by experimentation on known black holes, like for example, CCLP. You just calculate its charges. You like the spinor was explicitly constructed in that case.
Yes, I see that. Well, yeah, I see this as I see the existence of killing spinner as a sufficient condition because, of course, if
Yeah,
you're supersymmetric, you must satisfy BPS bound, but
yeah.
vice versa.
Vice versa. So what I can actually say about this, and quite more confidently, is that this condition is actually should be viewed in spaces which are asymptotically AdS, should be viewed as a anti-commutator between fermion generators in the superconformal algebra.
Mm.
And those guys are well-defined things, and the anti-commutator of those guys is equal precisely to something like this. So my intuition really and the logic of the paper really was to get what field theory is telling me that my charges should be doing at supersymmetry and impose this.
Mm-hmm.
And cross our fingers, but there is not significant need for crossing because it will happen, that this solution is going to be supersymmetric. Okay. So the Lord, we kind of like used field theory a little bit more than I guess than I advertised in the actual talk, but I think it's a fair game. This relationship has very significant field theory origins, and it signifies supersymmetry of the solution from the other direction. So this kind of like implication, if you wish, field theory is telling me that the arrow is going that way, and gravity is telling me that the arrow is going that way.
I kind of see it. Okay, I kind of start to believe you, but so is it an old result? What are the names after this paper, this result?
Uh, well, okay, so like the place where this was analyzed
Mm,
is those two papers. This one you're familiar with, of course.
I see, yeah. Mm-hmm.
And but of course that was analyzed in the special case of 5D supergravity.
Mm-hmm.
Uh, Hosseini, Christoph Zaffaroni have it in AdS7. But once this is a very generic statement that I'm saying that supersymmetry, the charges obey a linear constraint like this. This directly comes from the algebra of the dual CFT. You
No,
just have to.
yes, yes, of course. Sorry for interrupting. Yes, of course. This is no doubt, but I mean, vice versa. If you have a if you have a general solution in the bulk, which has charges satisfying this constraint, I don't
Yeah.
immediately see how all the integrability conditions for the killing spinner will be satisfied.
Okay, I see your point. Yeah. Okay. So, but I think then this implication you're gonna be a little bit happier with existence of spinor and this condition here. Because this condition, you can, if a spinor existed and you drag it along all of the U1s, you would find this here. And that's probably something that you can more easily relate to the integrability conditions that you're talking about on the Keller base.
Okay, yes, I see. Yes, I definitely see. I mean, both can be computed, both the middle and the right-hand side. Yes, so yeah, it can be checked.
Yeah, I'm not aware. Maybe somebody has done it, but I just don't know like of a good, very kind of like theorem level analysis of what you're asking for. But it's certainly something interesting to do.
Hmm. I see. Yeah. Well, I guess one can see it from asymptotic expansions, at least in a toric case. Well, one can compute the asymptotic quantities and then try to impose supersymmetry on expansions, vice versa. Yeah, that actually would be interesting.
Yeah.
Mhm. Okay. Well, thanks for answering my questions. Okay. So final questions one, final questions two. Okay, final questions three. Okay. Thank you again, Vasil, for a great talk.
Yeah. Thank you for having me. Yeah.
Yeah, sure. We're always happy to have you. Yes, so can I ask you to share your slides with me so that we can put it on the seminar webpage?
Yeah.
Okay, perfect. And the recording will be on YouTube.
Okay. Awesome.
Okay, awesome. Yes. Good luck. Good luck with your moving between cities and countries. Um, moving between peninsulas. Actually, it's Bulgaria.
Yeah. Yeah.
Yeah, I can say. Okay. So yeah, good luck and see you.
All right. See you. Bye, everybody.
Bye.